Okay, we'll start with chapter 1, measurements and units. The first thing is about units. The first SI units, or the basic SI units for the syllabus at all, is mass, length, time, temperature, and current. Mass is always in kilogram in SI units. Length is in meters. Time is in seconds. Temperature is in Kelvin, not degrees Celsius, not Fahrenheit. And the current has only one unit, which is ampere. The prefixes are the multiples of 10 or the powers of 10 multiplied by any value. For example, for 25 kilometers, the meter is a unit, the kilo is a prefix, and the 25 is the magnitude of the value. So we have many prefixes. The giga is 10 to the power of 9. Mega is 10 to the power of 6, which is 1 million. Kilo is 10 to the power of 3, 1000. Now we go to the lower prefixes. Santi is dividing by 100, so it's 10 to the power of negative 2. Milli, 10 to the power of negative 3 divided by 1000. Micro, the symbol for micro is this, it's called mu. It's 10 to the power of negative 6 or divided by million. Nano is n divided by a billion, 10 to the power of negative 9. To convert from one prefix to another prefix, for example, we have 300 micrograms, and we need to convert it to kilograms to write it in SI units. So we check the powers of 10 of the old prefix and the power of 10 of the new prefix. We have 6 and 3. We take the magnitude, we multiply it by 10 to the power of the old power minus the new power. So the old power is 6 minus the new power is 3. Sorry, negative 6 minus negative 3. So the final value will be 300 times 10 to the power of negative 9. Negative 6 minus 3. So this is how you convert from a prefix to another prefix, times 10 to the power of the old prefix power minus the new prefix power. Okay. Now to check how to use significant figures. For example, you have an equation which requires using two values or two numbers, and each value is written to a different amount of significant figures. For example, 50.00, that's 4 significant figures. Any zero on the right after the decimal point, you have to consider a significant figure. But if it's before the decimal point, for example, 200 can be considered 1 significant or 2 significant or 3 significant. Okay, to write the answer, it would be 2. 50 divided by 25 is 2. But we use the minimum number of significant figures. So we can write it as 2.0. We cannot write 2 alone, since it's 1 significant figure and the minimum number is 2 significant figures. We can also write 2.00, which is 3. We are allowed 1 more significant figure other than the minimum number. So 2 significant here or 3 significant figures. We have also to remember which measuring device to use when measuring length. For example, for a ruler, we have to choose between 0 and 50 centimeters that we can use a ruler. For anything larger than 50 centimeters but less than 1 meter or within 1 meter, we use a meter rule. Anything greater than 1 meter, we use a measuring tape. If we can't have an accurate measurement, for example, very small length or very small diameters or something like that, we need to multiply the number. If you increase the reading, the error decreases, because we say that the percentage error decreases. You cannot just say to make it more accurate or to have a more accurate measurement. You must say to reduce percentage error. For example, you want to measure the circumference of a pen or a rod. You can measure the circumference 6 times or 10 times, then divide the measured length by the number of turns. For example, if you did a length of 70 centimeters or 70.0 using a meter rule or a ruler, you then divide by the number of turns. If it's 6 turns, you divide by 6. If it's 10 turns, you divide by 10. Or you can use 2 blocks. These questions could be said in paper 4 or paper 6. so you can use it in both papers. Say you want to measure the diameter of one ball bearing or one ball, but you have identical ball bearings. You can place them right next to each other and measure the total length looking perpendicular to the scale, and then subtract the two readings to get the length of all the ball bearings. Then you divide by the number of bearings. As for the types of errors, we have parallax error, and you can correct a parallax error. It's also called line of sight error. You can fix it by looking perpendicular to the scale, and you can use this with rulers, protractors, thermometers, or measuring cylinders. Anything with a scale, you can say you can avoid parallax error by looking perpendicular to the scale, either in paper 4 or in paper 6. As for gap error, you can say that you can place the ruler or the measuring device as close as possible to avoid gap error. Any gap error causes the readings to be too small or smaller than the original value. As for end errors or zero errors, you can know the amount of error in the reading and then subtract it. For example, in this reading, the measurement is 9.3 centimeters, but there is an error of 2.0 centimeters. So you subtract 9.3 minus 2, you get the real value. So we have 3 errors in measurements of length. Specifically, parallax error, you can fix it by looking perpendicular to the scale, and gap error, you can fix it by placing the measuring device as close as possible, and the end error or zero error, you can subtract it from the reading. You are also required to memorize the equations for calculating volume and area. For example, volume of a cube, if it's of side L, the volume will be L cubed or L to the power of 3. If there is a cuboid with a length L, width W, and height H, you multiply all the sides by each other. So L times W times H, you get the volume. If there is a sphere with a radius R, you get the volume 4 over 3 pi R cubed. If you have a cylinder, which is basically a circular cross-section with a height, if the circle has a radius R, there is a general rule for volume. You can calculate it by multiplying the area by the height or the length, which is perpendicular to the area. In this case, the area is pi R squared, area of a circle. Then you multiply it by the height to get the volume. For a triangular prism, there is a base, which is one side of the triangle, and there is the line which is perpendicular to the base, which we call the height, and there is another height, we can call it thickness. In this case, the area is a triangle, so half base by height, then you multiply it by the thickness, area multiplied by another length which is perpendicular to the area. For a square, the area is the length squared. For a rectangle, you have length by width. Now we go to the units of volume. If you have a volume of 1 centimeter cubed, and you need to use SI units, for example, in using forces, pressure, energy, power, in electricity also, you must use the SI units. So you must convert 1 centimeter cubed to 1 meter cubed. But 1 centimeter cubed, if you want to convert centimeter into meters, you divide by 100. So if you want to convert centimeter cubed to meter cubed, you divide by 100 cubed. If you have an area of 1 centimeter squared and you want to convert it into meters squared, you divide by 100 squared. Now, if you have a volume of 1 millimeter cubed, you divide millimeter by 1000 to get meter. So to get meter cubed, you divide by 1000 cubed. Same for area, for 1 millimeter squared, you divide by 1000 squared to get meter squared. When measuring volumes using a measuring cylinder, you have to make sure that the cylinder is vertical. You have to look perpendicular to the scale. If you're required to draw a line of sight, you draw a dashed line at the bottom of the meniscus of the liquid, and the I symbol is just curves like this with an iris. So you draw it perpendicular to the scale at the bottom of the meniscus, and make sure that the cylinder is vertical before reading and clean before reading. As for measuring the volume of an irregularly shaped object, you can just say first fill the measuring cylinder or half fill the measuring cylinder with some liquid and record the initial volume, volume 1, then immerse the object in the liquid, the volume level will rise, you measure the new volume, you can call them V1 and V2 or VA and VB, then you say you should calculate the difference in volume, so V2 minus V1. We use the symbols just to shorten our sentences in the answer. If the object is too large to immerse in a measuring cylinder, we can use something called a displacement can with a spout. The displacement can will remove any water excess when you add the object. So the volume in the measuring cylinder that you collect from the spout is equal to the volume of the object. So if a large object is said to be measured as a volume, you need a displacement can and a measuring cylinder. Okay, which measuring cylinder to use? It's always better to use a narrow cylinder, since the spacing between the divisions will represent smaller numbers. Or you can say that a narrow measuring cylinder is more precise or more accurate than a wide cylinder. So for example, a cylinder is better than a beaker because the beaker is wider. As for masses, we have many devices. This one is called a top pan balance. A top pan balance is better when it's digital because it can read any value and it is accurate to either grams or 0.1 grams or 0.5 grams. For a beam balance, you have specific weights to use, which means it's not very accurate, but it is not affected by gravity. A top pan balance is affected by gravity, but a beam balance is not affected by gravity. So it's better when you're not sure if the gravity field strength is the same. For example, if you want to measure mass on another planet or on the moon, you would use a beam balance instead of a top pan balance. So for measuring mass of liquids, you can not just pour liquids on top of a balance. You must use a container, so you must measure the empty container first. Then you measure the mass of the container and the liquid inside. For example, you name this M1 and you name the second one M2. Then you calculate the mass of the liquid by subtracting M2 minus M1. For measuring time, there is always one particular error, which is you cannot call it just human error. It's called human reaction time or human reaction error. When you're measuring any time, you must account for this error and you must repeat and then take an average to reduce the amount of this error. It cannot be completely removed. It just can be reduced by repeating and averaging. For any experiment, you can say when measuring time, you should repeat and take an average for the time. Say if you are required to measure the time for a repeated event like the swinging of a pendulum, you can say some precautions. You can say that you should define a marker, a position to count from the swings. So every time the object reaches this point, you count 1, 2, 3, and so on. Then you release it and measure the time for several swings or several oscillations or several cycles instead of one cycle to reduce the percentage error. Then you repeat and take an average. Then you divide by the number of cycles. It's better to divide after calculating the average instead of calculating the average many times for each oscillation, or dividing by the number of swings each time you measure, then you calculate the average. It's better to leave the average at the end. The last part of chapter 1 is calculating density. Density is defined as the mass per unit volume, and you can just say the equation when you're required to define density. You can just write down density is equal to mass over volume, but you should use words in the definition unless the symbols are mentioned. The usual symbol for density is called rho. It's not D, but you can use it when calculating or when you're required to calculate some volume or density or mass using the equation. So rho is equal m over v or d equal m over v, and we have two units: gram per centimeter cubed and kilogram per meter cubed. To convert from gram per centimeter cubed to kilogram per meter cubed, you must multiply by 1000. To go from gram per centimeter cubed to kilogram, you multiply from kilogram per meter cubed to gram per centimeter cubed, you divide by 1000. So if you have something that is less dense than a liquid that is swimming on, the object will float. If the density of the object is less than the density of the liquid, the object will float. If the density of the object is more than the density of the liquid, the object will sink. Okay, the second chapter is motion. First, there is a difference between something called vector quantities and scalar quantities. Vectors are quantities that have magnitude and direction, like displacement, velocity, acceleration, forces, momentum, moments, current also. Scalar quantities, these are quantities that have magnitude but no direction. Another similarity between vectors and scalars that they both have magnitude and unit, not only magnitude. Okay, for adding scalars, you can just add using the calculator the plus sign, or subtracting, you can just subtract easily. But when dealing with vectors, you must do it graphically. You either use a parallelogram addition diagram or a head-to-tail addition diagram. For example, we have here two vectors called A and B, and you want to add them using a parallelogram method. You must know the angles from a horizontal reference or a vertical reference. For example, you have this point we will call alpha, this point we will call beta, these two angles. So first you must draw a horizontal line as a reference to measure the angle alpha and measure the angle beta. If you're drawing a parallelogram, you start from the same point. This is the start of the diagram. And you must choose a scale enough to fill the empty space in the paper, just to make it more accurate. Then you add another line which is parallel to each of the vectors. So this is parallel to this one. And you close the diagram on the other end. Either you use angles or a compass or a set square and a ruler to draw the parallels. You're free to use whatever you want. You just have to make sure that the sides are parallel to each other and the general shape is a parallelogram. Sometimes when people draw parallelograms, you end up with something like this. For example, like this. This is not a parallelogram. This side is not parallel to this side, and this side is not parallel to this side. You must make sure that you've drawn a parallelogram correctly to get the resultant. Now you've crossed the lines and you got the end of the diagram. You must mention the directions of the original vectors and the direction of the resultant vector from the starting point of the diagram to the ending point. For example, you multiplied everything by 2. When you multiply everything by 2, for example, you have here 40 newtons and 20 newtons, or make it 4 and 2. 4 newtons and 2 newtons, and you want to draw longer lines to fill the space. You draw this one to be 4 centimeters and you draw this to be 8 centimeters. What is the scale? You take one of the forces or one of the vectors and you say if 4 newtons is represented by 8 centimeters, what does 1 centimeter represent? And then you do cross multiplication, then you get the scale. For a head-to-tail addition, you have the same vectors A and B, but you do not start from the same point. You pick a starting point you draw one arrow, and at the end of this arrow, you draw the second arrow. Until you reach the last point of the arrow, this is the end of the diagram. You just connect the start to the end. And also using a scale, or you can just use a scale 1 to 1 if the numbers are large enough or small enough to fit the empty space in the page. When dealing with subtracting vectors, for example, you want to subtract the resultant -1 of the vectors. For example, it is said that this is the resultant of two velocities, and this is one of the velocities. This is velocity 1, and this is the resultant velocity, and you want to know the other velocity v2, which is unknown. For defining a resultant vector, it is the sum or the addition or the net of the vectors. So the resultant vector should be equal to v1 plus v2 as vectors, not as numbers. If you want to get v2, you should subtract v resultant minus v1. But negative v1 is the opposite of v1. This is negative v1. Again, drawing a scale diagram, you can draw first the resultant because it is the positive one. You know the angle, so you draw the first one, and you must use a head to tail method. You cannot use a parallelogram when dealing with subtraction. So at the end of the first vector, you draw the second vector, but in the opposite direction. It should have been pointing upwards and to the right. Now it's pointing downwards and to the left. So this is the resultant vector. This is negative v1. So this was the start of the diagram. This was the end of the diagram. You connect the start to the end. So this is vr minus v1. That's how you do subtraction. You do a head to tail addition, but you reverse the one with the negative sign. If you have parallel vectors, for example, you have 2 meters per second and 1 meter per second, you just add using a plus sign. So it would be 3 meters per second pointing in the same direction. If the forces or the vectors are in opposite direction, for example, you have 2 newtons and 1 newton pointing in the opposite direction, you use minus sign. So 2 minus 1, you will get 1 newton, but in the direction of the larger force or the larger vector. So the larger vector was pointing to the right, so the resultant would be pointing to the right. Now we go to the motion quantities. Speed is generally defined as distance traveled per unit time, but it is not always measured or calculated using this equation. You can only use this equation if it's constant speed, or you're required to measure or calculate the average speed, which is the total distance divided by the total time. So you can only use this equation if the velocity or the speed is constant, or you are required to calculate the average. And the unit is meter divided by second, or we write it as meter per second. If you want to convert kilometers per hour into meters per second, you divide by 3.6. And the opposite, if you want to convert meters per second into kilometers per hour, you multiply it by 3.6. As for velocity, the definition of velocity is displacement divided by time. It is the same concept, but displacement has a direction. Distance does not have direction, and the unit is still meters per second. If you're required to define speed, it is a distance traveled per unit time. If you want to define velocity, it is the displacement per unit time, or you can just write the equation, displacement over time. Now we come to acceleration. The definition of acceleration is the rate of change of velocity or change in velocity over time. Also, to define something in paper 4, you must write it in words, not in symbols. If you use symbols, you must mention the symbols. For example, delta V here is the change in velocity, T is the time. And you can split this up. Delta V can be written as V minus U, or v2 minus v1, always final minus initial. If the acceleration is positive, this means that the speed is increasing. If the acceleration is negative, this means that the speed is decreasing. If you are required to calculate the deceleration, write the equation as it is. You will get a negative magnitude. Then you write the answer without the negative. And the unit of acceleration is meters per second squared. As for constant acceleration, if something is said to be accelerating at a specific number in meters per second squared, or it clearly says in the question that there is a uniform or steady acceleration or constant deceleration or something like that, you have an option to use any of the following equations. V, final velocity, equals u plus at, initial velocity, plus acceleration multiplied by time. S, which is the displacement, equal to the average velocity, v plus u, the average of the initial and final velocities multiplied by time. You can also use s equals ut plus half at squared, or v squared equals u squared plus 2as. According to the number of givens, or which givens are given in the question, you should have 3 givens and 1 unknown in the question, and 1 will be missing. Each one of these equations have something missing. For example, the first one you don't have s, the second one you don't have a, the third one you don't have v, the final velocity, and the last one you don't have time, t. According to the missing given or the missing variable, you should use the equation that does not have that missing variable. We have 2 examples here. If a car initially moving with velocity 12 meters per second, you have the initial u, accelerates uniformly at 3 meters per second squared. This is the unit of acceleration. What is the final velocity? So the unknown is v. After 5 seconds, you have time. So we have time, acceleration, initial velocity, and final velocity. There is no mention of distance. So we should use an equation that does not contain s. So we use v equal u plus at. Another example, if the car's velocity is decreasing at 3 meters per second squared, we say that the acceleration equals negative 3. The car is said to be decelerating at negative 3 meters per second squared, okay? And you still have the initial velocity, the acceleration, and the final velocity is required. You use the same equation. So according to the givens, you must look for 3 givens in the sentence. If it says that you started from rest, the initial velocity is 0, u equals 0. If it said that the car stops, the object stops after some time, stops means that the final velocity is 0. As for motion graphs, there are 2 types of graphs used in paper 4 or paper 2. There is the distance time graph, so you have distance on y-axis and time on x-axis, and the slope or the gradient of the graph is equal to the velocity. So whenever you're required to calculate the velocity from a distance time graph, you say that the velocity is equal to the gradient, and you calculate it using y2 minus y1 over x2 minus x1. Okay, for an object at rest in a distance time graph, you will see a horizontal line. For constant speed, you would see a straight line. And if you have a steeper straight line, this means that the velocity is greater. This is a low velocity, this is a high velocity. For an accelerating object, means that the speed is increasing, so the gradient or the slope should be increasing, which means the line will become more vertical as you go with time. As for a decelerating object, this means that the gradient will be decreasing, so the line will become more horizontal as you go with time. And again, if you want to calculate the velocity, you get the gradient. You must mention this relationship if you have a graph. You do not use the equation if you have a graph with all the values given on the y and x-axis. For a speed time graph, this means that the speed is on the vertical axis, y-axis, and time on x-axis. And here the slope is equal to the acceleration. So if you're required to calculate the acceleration, you say acceleration is equal to the gradient and you use y2 minus y1 over x2 minus x1. You do not need to use, actually you have to use the gradient of the graph to get the acceleration if it's a speed time or velocity time graph. For an object at rest in a speed time graph, it's also a horizontal line, but it must be on the x-axis. It must be horizontal at speed equals 0. For a constant speed, you have a horizontal line that is not at speed 0. For accelerating object, for a uniform acceleration or constant acceleration, that means there is a constant gradient. So you have a straight line. So whenever you calculate the gradient at any point, you can use any 2 points. You will still get the same result, the same constant acceleration. For constant deceleration, still the gradient should be constant, but the speed should be decreasing. So you have a negative gradient. So a constant gradient with positive value, you have accelerating object. A negative gradient with a constant value, you have a decelerating object, and it's said to be constant or uniform acceleration or constant deceleration. You cannot just answer accelerating or decelerating. You must say constant acceleration if it's a straight line. As for a changing acceleration, an increasing acceleration means an increasing gradient with a positive value. So the speed should be increasing and the line should become more vertical with time. For a decreasing acceleration, you have an increasing gradient, decreasing gradient, but still the gradient is positive, so the speed increases and the line becomes more horizontal with time. Deceleration means the speed decreases with time. Increasing deceleration means the line becomes more vertical. Decreasing deceleration means the line becomes more horizontal. As for the distance, you can calculate the distance using the area under the graph, which is the area between the line and the x-axis. This is the area under the graph in a speed time graph. There is no area under the graph in a distance time graph. You can only calculate distance from a speed time graph using the area under the graph. If you have an irregular curved line and you want to calculate the slope or the area, for a slope, for example, you have this curve and you want to calculate the gradient at this point. For example, this is a distance time graph and you want to calculate the speed. You must draw a tangent line to the curve and use that line to calculate the gradient. Then you choose 2 points. This is point 2, so you get y2. This is point 1, you get y1, and you have x1 and x2. Then you calculate the slope. Also, if you have an irregularly shaped object or graph and you want to calculate the area under the graph, for example, this is a speed time graph and you want to calculate the area below the graph, you can just divide the graph into vertical sections, equally spaced vertical sections, and consider the line at the top to be straight. For example, this part straight, this part straight, this part straight, and so on. And then you have trapezium rule to calculate it. For example, this is the first base, base 1, and this is base 2, and this is the height for the first area. And you have area 1, area 2, area 3, 4, 5. Then you add these areas together to get the final area. It is not an accurate or an exact value, but it is an accepted value. And you have a large range of acceptable answers in this case. Another way of calculating the area under the graph is to just draw a line horizontal, like for example at this position, and see if the area above the line and the area below the line, this area should be entered in the answers and this area shouldn't be removed from the answer if you want to calculate the rectangle below the line. If these areas are equal, just calculate the rectangle area below the line. If they are not, for example, in this case, the upper area is smaller than the lower area, so you move the line downwards a little bit. Now these areas are almost equal. Now you can calculate the area of the rectangle below the line. This is also not an exact value, but it will give you an acceptable value within the range of the exam. There is something called free fall acceleration or gravity acceleration. The gravity acceleration on Earth, you should memorize it as 9.8 meters per second squared, and you should know that it is always pointing downwards. If an object is falling downwards, you say that the acceleration is equal to positive 9.8. If the object is projected, thrown, not pushed upwards, thrown or projected upwards, the acceleration would be negative 9.8 meters per second squared. So you can have an object within a question. It said an object is dropped. Dropped means, or released means, that the initial velocity is 0 from the top of a window and it travels for 3 seconds. It appears that you have only one given, which is the 3 seconds, but actually dropped means the initial velocity is 0, and since it is falling, you have an acceleration of 9.8 meter per second squared. Or an object is projected upwards with a velocity of 30 meters per second. It reaches the maximum height. Again, it appears that you have one given, which is the 30 meters per second initial velocity, but since it is projected upwards under gravity, the acceleration is negative 9.8, and maximum height means that the final velocity will be 0. So you actually have 3 givens. Okay, the next chapter is forces. For a force, you have to know that it is the rate of change of momentum. You can measure it using a spring balance or a Newton meter. A force can change the motion of an object or the shape of an object. For the motion, you say that it can change the direction of motion or the speed of motion. If you want to split the motion, you can say that a force can speed up or slow down an object or change the direction. For the shape, you can change the shape or the size of the object. You can make it longer or shorter or wider, but it cannot change the mass of an object. This is a constant. You cannot change a mass using a force. As for calculating a resultant force, is the same as in vectors in general. You can add parallel forces if they are pointing in the same direction, subtract parallel forces if they are pointing in opposite directions. There is a special case when the forces cancel each other. For example, these two forces, 2 newtons and 2 newtons, cancel the 4 newtons from the other side. You say that this object will not accelerate. If it is at rest, it will remain at rest. If it's moving, it will keep moving with constant velocity. If the forces have an angle between them, you can use the parallelogram method, or you can use the head to tail method to add the forces. Okay, for example, this is from the start to the end. This is the resultant of these two forces. There are 3 laws called Newton's laws of motion. The first law is called the inertia law, or the first Newton's first law. It states that if there is no resultant force acting on an object, not just no force, there could be forces that cancel each other, the object will remain at rest if it's already at rest, or will keep moving with constant velocity, which means constant speed in a straight line in the same direction. The second law is the relationship between acceleration, resultant force, and mass. For a constant mass, if you increase the force, you increase the acceleration directly proportional. So the graph between acceleration and resultant force is a straight line through the origin. As for constant resultant force, if you increase the mass, the acceleration decreases. So this is a curve that looks like this. This is an inverse relation. Mass and acceleration are inversely proportional. Or if you draw 1 over mass with acceleration, you will have a straight line that goes through the origin. If you're required to mention or state Newton's second law in words, you say that the acceleration is directly proportional to the force and inversely proportional to the mass, but the force must be a resultant force. For example, if you want to calculate an acceleration of an object with these through 3 forces, you have to calculate the resultant force at first, 11 minus 2 minus 3. Then you divide that resultant force by the mass to get the acceleration. Using the equation, acceleration is F over m, or as you may know it, F equals ma. But when you're using this equation, you must use the resultant force, the mass in kilograms, not in grams, and the acceleration will be in meters per second squared. This is a must. You must use in kilograms, and this must be the resultant force. If there is only one force on the object, you just use that one, but you must check the question if there are other forces mentioned in the question or not. Newton's third law states that for every action there is an equal and opposite reaction. For example, if object 1 acts with a force on object 2, object 2 will react with an equal and opposite force. For example, here F12 is equal in magnitude to F21, from 1 to 2 and from 2 to 1, and one of them has a negative direction. As for types of forces, we have many types of forces. The first one is the gravitational force, or we can just call it the weight. The weight is defined as the force of gravity or the attraction force due to an object mass or due to a gravitational field. And these forces are action and reaction. For example, the earth pulls someone towards it, and as a reaction, the person pulls the earth towards him or her. So these are action and reaction forces, and they are equal in magnitude. If the astronaut is pulled by 900 newtons, the earth is pulled towards the astronaut by 900 newtons in the opposite direction. But since the mass of the astronaut is much less, they will accelerate with a greater magnitude. As for the gravitational field strength, it's called G. On Earth, every 1 kilogram of mass experiences a force of 9.8 newtons. So we say that the unit of the gravity field strength, newtons per kilogram, 9.8 newtons for every 1 kilogram. And it is also equal to the gravity acceleration, which is 9.8 meters per second. So we have two units for the gravity field strength, Newton per kilogram or meters per second squared. And we use that field strength to calculate the weight. The weight is equal to mg, the mass in kilograms multiplied by the field strength in newtons per kilogram or meters per second squared. For example, if the gravity field strength on the moon is 1.6 newtons per kilogram and you have a weight of 50 kilograms, you multiply 50 by 1.6 and the answer will be in Newton since this is a force. This leads to a differentiation between mass and weight. There are several differences, and there are actually no similarity except that they both depend on the amount of matter in an object. If you want to define mass, it is a quantity of substance in an object or a property that resists change in motion. If you are heavier, it is more difficult to move you. As for the weight, it is a force on a mass due to gravity or due to a gravitational field. The units are kilograms and newtons. The measuring devices, for mass, it's a regular top and balance or a beam balance. For weight, it's a force, so you use a spring balance, or you use a balance, then you multiply by g. As for mass, if the object does not change, the mass does not change. But for weight, it depends on the value of g. If g increases, the weight increases. If g decreases, the weight decreases. Next, we have the normal reaction force. It is the reaction of the push on something. If you push down on a surface, for example, if there is a force pushing in this direction, there is a reaction in that direction, perpendicular to the surface. It's always perpendicular to the surface. So this book is resting on a horizontal surface, the reaction would be vertical. So this reaction prevents the book from actually going down due to its weight. Now we go to friction. Friction is basically caused by imperfections in a surface. What increases friction? If the roughness of the surface increases, or the contact area increases, or the mass of or the reaction force on the object increases. Friction also has two effects. It has heating effect and a wearing effect. The molecules actually fly off a surface when you slide surfaces against each other, when you rub surfaces against each other, they lose some of their molecules. We call this wearing effect. And the work done during the sliding causes the heating. To reduce friction, you either use lubrication, which is adding liquid between two surfaces, or you use roller bearings or any rolling object or circular object between the two surfaces. This decreases the contact area. If you're asked why roller bearings or rollers decrease friction, because it decreases the contact area between the two surfaces. And friction in liquids is less than friction in solids. That's why lubrication decreases friction. In recent questions or in recent exams, you are required to mention something called the thinking distance and the braking distance or the stopping distance of a moving vehicle. If you draw a velocity time graph for a vehicle with a driver that sees an obstacle then decides to hit the brakes, during the reaction time, the velocity of the vehicle does not change. This is called the thinking time. Then, once you hit the brakes, the speed of the vehicle decreases. If the braking force is constant, you have a constant deceleration until you stop. And the area under the graph is equal to the distance traveled. So this is the thinking distance or the reaction time distance, and this is the braking distance, and the total is the stopping distance. So what decreases or increases the thinking distance? If you are under the effects of alcohol, drugs, or stress or tiredness, the reaction time increases, and so the thinking distance increases. If the braking system of the car is faulty, or there is a wet road that decreases friction, or icy road, or the tires are worn off, for example, if you keep using the same tires for several years, eventually they will become, we call it bald tires. There is no friction or less friction than before. That decreases the friction force and decreases the deceleration. In many questions, you are required to describe the motion of a falling object, but with the effect of air resistance, or a falling object in a liquid. So you have liquid resistance or drag force. And you always start saying that at the start, if you are released from rest, the acceleration is equal to the gravity acceleration, since there is only the weight acting on the object. But as speed increases, the drag force or the air resistance increases. So now you have two forces opposing each other, weight and drag. And as drag increases, the resultant force, which is weight minus drag force, so the resultant is weight minus drag, decreases or increases according to the drag. If the drag increases, the negative sign increases, so the resultant force decreases. And according to F equals ma, as resultant force decreases, acceleration decreases. That's why the velocity time graph has a decreasing gradient. Acceleration decreases as resultant force decreases. Until you reach this point where the weight is equal to the drag force, so resultant force equals 0 and acceleration is equal to 0. If the falling object has a parachute, at this point a parachute is open, the area increases. Now the drag force is greater than the weight. So the resultant force and acceleration are opposite to the motion. So speed decreases. But as speed decreases, the drag force decreases. Now the drag force is in the direction of the resultant. If the drag decreases, the resultant force decreases. So as the resultant force decreases, the deceleration decreases. That's why the gradient of the graph keeps decreasing. So first we have decreasing acceleration until you reach constant speed. Now we have decreasing deceleration until you again reach constant speed when the drag force is once again equal to the weight. Until you reach the ground and your speed drops to 0 suddenly. So we must memorize these sentences. As speed increases, drag force increases, resultant force decreases, and acceleration decreases. After the parachute is open, if there is a parachute, the area increases, so the drag force is greater than the weight. So there is a resultant force against motion. So speed decreases. As speed decreases, drag decreases, and the resultant acceleration decrease until terminal velocity. At terminal velocity, the first terminal velocity before the parachute and the second terminal velocity after the parachute, the weight is equal to the drag force, so there is no resultant and no acceleration. Now we go to springs and elastic and plastic behavior. An elastic object means that if you deform the object using a force, then you remove the force, the object returns to its original shape and dimensions. Plastic behavior is the opposite of this sentence. If you remove the deforming force, the object does not return to its original dimensions or shape, which means that it is permanently deformed. In many exams, you were required to describe an experiment to measure the extension of a spring. First, you hang the spring from any object or from a clamp. Then you place a ruler or a meter rule right next to it. You can say that you use a set square to make sure that the ruler is vertical. And look perpendicular or use a pointer to measure the distance or the length of the spring. First, you measure the original or the unstretched length of the spring, then you measure the extended length, and to measure the extension or calculate the extension, you subtract the extended length minus the unstretched length or the original length. You can write it as x, the extension, is equal to the new length L minus the original length L naught or L0. In this experiment, you are required to mention several precautions, using set square to make the rule is vertical, looking perpendicular to the scale, or using a pointer to show the reading. Place the rule as close as possible to the spring. In this experiment, the result was that if you increase the force on a spring, the extension increases, and we got Hooke's law. If you are required to mention Hooke's law or state Hooke's law, the extension of a spring is directly proportional to the force applied. So we have extension and force, not the length and force, it is the extension and force directly proportional, which means if you draw a graph of force against extension, you have a straight line through the origin. But if you draw force against length, you will not get a straight line through the origin. It will be a straight line, but not through the origin. You will still have the original length to start from, and then it will be a straight line. There is something called the spring constant. If you want to represent this law using an equation, you say that the force F is equal to a constant, which is called the spring constant or the force constant K, multiplied by the extension, which means that K is equal to force over extension. You can get it directly from a force extension graph. You can use the axes to get a value for F and a value for X, then use the equation directly. And the unit would be the unit of force, which is Newton, divided by the unit of the extension. If there is an extension on the axis in centimeters, you say that it is newtons per centimeter. If the extension is in millimeter, it's Newton per millimeter. In the case of a force length graph, you must subtract first the original length. For example, if you go from this force and you find this length, this is not the extension, this is the new length or the stretched length. Then you have to calculate K as equal to F over L minus the original length. And the original length is always at the force equal to 0. That's how you find the original length on the graph. While extending a spring, there is something called the limit of proportionality, and there is another thing called the elastic limit. They are not the same. The definition of a limit of proportionality, it is the point after which the spring no longer obeys Hooke's law, which means if you draw a force extension graph, there will be a part that is straight line through the origin, but after that point, which is the limit of proportionality, the graph will curve towards the extension axis, which means if you reverse the axes, this is extension and this is force, you will still have a straight line through the origin. Then after a certain point, the graph will curve toward the extension axis, always towards the extension axis. What is meant by an elastic limit? It cannot be shown on a graph, but it is consider the same point on the graph. An elastic limit is the point after which the spring does not return to its original dimensions, which means before that point, if you remove the force, the spring returns to its original unstretched length. After that point, if you pass this point, the spring will not return, it will return like this, and there will be a permanent extension or permanent deformation. The last part in springs is if you connect springs in series or in parallel. Series means one behind the other or one below the other. In parallel means one next to the other. So if you have one spring, if you pull it with a force F and it causes an extension X and it has a spring constant K. If you use the same force on two springs, you will get double the extension, which means you have half the spring constant. That means that it is weaker now. It is easier to extend. The same force give double the extension. If you have springs that are in parallel, connected from one side, and you pull them together from the other side, if still one spring has a spring constant K and you pull it with a force F and you get an extension X, if you pull the same spring but twice or two springs that are side by side, this force is divided on the two springs. So this will get half the force and have half the extension. This will also have half the force and get half the extension. But these extensions are parallel to each other, so the total extension is still x over 2. If you are getting half the extension, this means you are having twice the spring constant. This means you have a stronger spring. So in series, you divide the spring constant by 2 and the extension multiplied by 2. And in parallel, you multiply the spring constant by 2 and divide the extension by 2. They are opposite to each other. If you have a spring or a rope or someone pulling something using their arm, you say that the force in these objects is called the tension force, which is the force inside an object. If you have a boat or something that is floating on the surface of a liquid, the force that stops something from sinking is called the upthrust or the upward force in a fluid. If you have an object that is moving in a circle, you must say that it is accelerating. Why is it accelerating? There is a change in direction, which means that there is a change in velocity, not in speed. Even if you are moving with constant speed, still the direction changes. This means that the velocity is changing, and since acceleration is the rate of change of velocity, there is acceleration. So if you have an acceleration, there must be a force, a resultant force. If an object is moving in a certain direction and you push it with a resultant force in the same direction, the speed of the object increases. If an object is moving in a direction and you pull it against its motion, the speed of the object decreases. But if you apply a force that neither pushes the same direction or pulls in the opposite direction, it's perpendicular to the motion. If it's 90 degrees with the velocity, then you have a change in direction without changing speed. So many times you are required to say or draw an arrow for an object moving in a circle, and this is the velocity, it's tangent to the circle, and you're required to draw an arrow to represent the resultant force on the object. It is perpendicular to the velocity. And if you draw several arrows that are perpendicular to the velocity along this circle, these arrows will always point towards the center of the circle. So we call it a centripetal force. It is not a type of force. This centripetal force could be due to gravity. For example, in a planet orbiting around the sun, the force that is pointing towards the sun is the gravitational force between the planet and the sun. If it's an electron orbiting around the nucleus, it is the electric force, the attraction between negative and positive. If you have a car and it's going in a circle, the sideways friction is the centripetal force. So the centripetal force is not one of the forces or not one of the types of forces. It could be any force, but it is the resultant that points toward the center or perpendicular to the velocity if you are moving in a circle with constant speed. If for some reason the force is suddenly cut off, the object will keep moving in a straight line without changing direction. Since there is no more resultant force, so according to Newton's first law, it will keep moving with constant velocity in the same direction. And the resultant force moving in a circle is equal to mv squared over r. If mass or speed increases or radius decreases, you need to bend more. The change in velocity is greater, you need a greater force. Okay, chapter 4 is about momentum. First, the definition of momentum, it is how difficult to change the motion of an object, or you can just write the equation that the momentum is equal to mass multiplied by velocity, or product of mass and velocity. The mass must be in kilograms and the velocity is in meters per second. So the unit is kilograms meter per second, or there is another unit from another equation, Newton times second, not Newton per second. It is a vector quantity, it has a direction. You can also use a vector diagram to add momentum. Not only velocities and force, you can also add momentum using a vector diagram in parallelogram method or head-to-tail method. There is something called an impulse or the change in momentum. The change in momentum is equal to the final momentum minus the initial momentum. You can call momentum P and the change in momentum delta P, and the impulse is called I as a symbol. Impulse is also defined as the force multiplied by time. Whenever you are asked to define momentum, you are required to say that it is a product of force and time. But it is also equal to the change in momentum. So you can use either one in calculation, force multiplied by time or final momentum minus initial momentum, or you can say that it is the mass multiplied by the change in velocity. As for the definition of force, we mentioned that in the last chapter, it is the rate of change of momentum. It is not a push or pull. You must say that it is the rate of change of momentum or change in momentum over time. And it is equal to final momentum minus initial momentum over time, or mass multiplied by the change in velocity over time. This is another form of Newton's second law, because V minus U over T is actually acceleration. So F is equal to ma. So you can either solve a force question using ma or the change in momentum over time. So F is equal to delta P over T. Whenever there is a collision between an object and a stationary object, and there is no more motion after the collision, there is a significant force because there is a change in momentum, and the change in momentum exerts a force, which is equal to the rate of change of momentum. If you want to decrease the force, either decrease the change in momentum, which means move with a slower speed before you hit, which is probably not going to happen, or you increase the time of the impact. How do you do that in cars or in sports? You add objects that absorb the force by changing their shape. For example, the crumple zone, the empty spaces in a car that crumple or change shape when a car hits something, it takes more time if you change shape. So during the deformation, the time of impact increases, so the force decreases, since the rate of change of momentum decreases. Another safety feature in vehicles is the seat belts. The seat belts do not increase the time of impact. They exert a backward force on the driver or the passengers, because without that backward force, an object that is moving forward, it will keep moving forward and will either hit the steering wheel or the windshield of the car. So a seat belt exerts a backward force on the passengers, and the airbag deforms and increases the time of the impact, so decreases the force on the passengers. In sports, we use helmets and knee pads and elbow pads, anything that changes shape to increase the time of the impact. Whenever you have two objects moving and then colliding, and you are required to describe the motion before or after, for example, you're required to calculate velocities before or velocities after, you use an equation called the conservation of momentum. The concept of conservation of momentum says that the total momentum before a collision is equal to the total momentum after collision, or that the total momentum of a system remains constant. If there is no collision mentioned, you just say that the total momentum of the system remains constant if there are no external forces like friction or gravity or anything like that, or that they cancel each other. For example, a ball moving on a table, its weight is cancelled by the normal reaction from the table, so you consider that there is no gravity and no reaction because they cancel each other. Using this equation, we say that for two objects, m1, u1, that's the initial momentum of object 1, plus m2, u2, that's the initial momentum of object 2, is equal to m1, v1, plus m2, v2, the final momenta of object 1 and 2. If for any question there is an object moving in an opposite direction, you say that its momentum is negative in the equation. For an explosion, you have an object that is initially at rest, so the initial momentum for all objects is 0. And after the explosion, it's split into two objects. They must travel in opposite directions because you have two objects, mass 2 and mass 1, moving with velocities v1 and v2. So the total momentum is m1 v1 and m2 v2, but the total should be equal to 0. So one of them must be negative, and the magnitudes of m1 v1 should be equal to the magnitude m2 v2. So you have a magnitude of 20, there must be another magnitude of negative 20 to cancel each other and get a total of 0. Okay, chapter 5 is about turning forces or moments. First, the definition of a moment. It is the turning effect of a force and calculated by multiplying force and perpendicular distance from a point, or the turning effect of a force about a point. So the equation is equal to force multiplied by distance, but the perpendicular distance means if you have a force in this direction and this is the pivot or the point, you calculate the distance that is perpendicular to the line of action of the force. So you draw a distance with 90 degrees from the force. It's either given to you in the exam or you can use trigonometry to get it. For example, in one of the exams in November 22, there was a force pointing in this direction and there was a distance in this direction, for example, or an angle 60 degrees, and this distance was 2 meters, and you want this perpendicular distance to the force, and the force was, for example, 50 newtons. So you have an angle and you have the hypotenuse of this triangle. You use the sine or the cosine. You want the adjacent line, so you use cosine. Cosine any angle is equal to the opposite divided by the hypotenuse. So cosine 60 is equal to the opposite, the distance, perpendicular distance, divided by the hypotenuse, which is 2 meters. Then you get the perpendicular distance, you multiply 2 by cosine 60. That's how you get the perpendicular distance. If you are required to take moments about any point, that means calculate the resultant moment about the point, or we can use it with this symbol, resultant moment, sigma m. If you have, for example, many forces acting on an object, like 10 newtons downwards here, you have 8 newtons acting in this direction. So if, for example, the 10 newtons is actually at this point, 8 newtons downwards, 3 newtons downwards, and you have a pivot O, and the distances from point B to this force 2 meters, to O 2 meters, to this one 1 meter, and 3 meters to the last one. You need to calculate every force separately. You cannot add forces and add distances. So the 8 newtons has a perpendicular distance 1 meter. So you have 8 multiplied by 1. And you must calculate the distance from the pivot. So the 3 newtons have a total distance of 1 plus 3, 4. So 3 times 4. And the 10 newtons has a perpendicular distance of 2 meters, so 10 times 2. Then you see which of these create a clockwise moment or an anti-clockwise moment. You must think, how will this force push the object around this point, around the pivot? So for example, these two forces want to rotate this side. This is clockwise, in the same direction as the arm of the clock. This force, the 10 Newton, only wants to rotate the object anti-clockwise. So you say that this is the anti-clockwise moment. You can write anti-clockwise ACM. And the clockwise moments is the sum of these moments. This is the clockwise moments. Okay, ACWM and ACM. Then you calculate the resultant. You give one direction. For example, the clockwise moment would be positive and the anti-clockwise moment would be negative, or the opposite. You are free to choose whatever is positive and whatever is negative. The important thing is the opposite is negative. If you choose one side to be positive, the other side would be negative, and then you calculate the resultant. If the resultant moment is 0, the object will not rotate. This is called the principle of moments. So if you're required to state the principle of moments, if an object experiences no resultant moment, or if the clockwise moments are equal to or balance the anti-clockwise moments, there is no rotation. There will be no rotation. There is a special scenario or special case called equilibrium. If you are in equilibrium, there will be no resultant moment and no resultant force. Resultant moment equals 0 and resultant force equal 0. So those are the conditions for equilibrium, or the definition of equilibrium. No resultant force and no resultant moment. If there is no resultant moment, no rotation. And if there is no resultant force, there is no acceleration. Which means if you are at rest, you will remain at rest. If you are moving, you will keep moving in the same direction. And if there is no moment, you will not rotate or you will not spin while moving. Some cases come with two supports or two pivots. If you have two pivots, then you have two forces or two reaction forces, other than another force that causes a moment. So you have 2 points here, B and C, and there is a force, let's call it RB, and another force, called it RC, or tensions in some other cases. And both forces are unknown. If you don't know both forces, and for example, the first question you are required to calculate RB, you take the moment about point C. If you are required to calculate the force at one position, you consider the other position the pivot, and start with using clockwise moments is equal to anti-clockwise moments, or the resultant moment equal 0. So in this case, you would calculate the force RB multiplied by its distance from the pivot, and the weight of this man multiplied by the distance also from the pivot. But one is clockwise and the other is anti-clockwise, and the system is at rest or stationary or supported or held in position. All these sentences or words mean that you are in equilibrium. That's why you use clockwise moments is equal to anti-clockwise moments. So whenever it is said that an object is supported, in equilibrium, at rest, stationary, held in place, all these mean two things. Clockwise moments is equal to anti-clockwise moments about a pivot. In this case, we chose the pivot to be point C to get RB first. And if you are required to calculate RC, then you use the other condition for equilibrium, which is resultant force equal to 0. So the force is pointing upwards. In this case, RB plus RC is equal to the forces pointing downwards. In this case, it will be W. Other questions, the forces could be right and left. So the forces to the right are equal to the forces to the left. So any moments question that state that you are in equilibrium, or whatever means that you are in equilibrium, the first question or the first unknown, you use clockwise moments equal anti-clockwise moments, and then the other unknown, you calculate that the resultant force equals 0, forces upwards equal downwards, or to the right equal to the left. The last thing about calculating moments, if you have the same moment, same turning effect, but you need to decrease the force. If you want to decrease the force, you must increase the distance. That is the concept of using wrenches or lifts or winches that increase a distance of rotation in order to decrease the force. For example, in this nut, you need to create a turning effect to rotate it in this direction, which is clockwise. But the distance from the edge of the nut to the center, which is the pivot, is very small. If you want to decrease the force you apply, you must increase the distance, so the force decreases. So force increases when distance decreases, force decreases when distance increases. They are inversely proportional for the same moment. This is the condition. Okay. The next part is called center of gravity. The center of gravity, or the center of mass, it is the point in an object where the weight is assumed to act, or where the mass is assumed to be concentrated at. It is not the point where the weight acts. The weight is actually distributed, or the mass is actually distributed. We assume that the weight acts at this point because the moments balance at this point. If you balance the object on the center of mass, it will not rotate. This is another application of the principle of moments. How to get the position of a center of mass or a center of gravity? If you have a uniform object. A uniform object means that its center of mass is at the geometric center of the object. So for a rectangle, you connect the diagonals and the intersection is the center of mass. For a triangle, you connect the medians and the intersection is the center of mass. For a sphere or a circle, the center of the sphere or the circle is the center of mass. But if you have an irregularly shaped object, you should hang the object from several points and use a plumb line to draw a vertical line from each hole, and the intersection between the lines will be the center of gravity. In this type of experiment, you would get an error. You would get the lines pointing like this, for example, and you have a triangle, not an intersection point. The cause of this is the friction between the pin and the object, the friction between the plumb line and the object, or that you are facing in the wrong direction or pointing your line of sight in the wrong direction. So instead of pointing at this point, you mark the line at this point. Line of sight error or parallax error causes also a change in the position of the line in this type of experiment. The last thing about moments is the stability of an object. An object is more stable if it has a low center of gravity, most of its mass is near the ground, or wider base area, not contact area, base area. For example, if you have a car and these are the tires of the car, the contact area is the tires themselves, but the base area is between the edges of the tires. This is called the base area. If the base area is wide or the center of gravity is low, it makes it harder to topple over an object or for the weight to move outside the base area. So the object is more stable. So if you have a wide base area and low center of gravity, this is called a stable equilibrium if you are at rest. If you topple something over, it will return to its original position. If the base area is narrow and the center of gravity is high above the ground, this is an unstable equilibrium. If you tilt the object a little angle, a small angle, it will topple over, it will fall, it will not return to its original position. If you have a circular or round object at rest, this is called a neutral equilibrium, because you cannot say that a ball rolling over is actually falling. It's not falling, it's just rolling. The contact area is still the same, and the object cannot be said to be toppling over. Next chapter is about work, energy, and power. Work is defined as the force multiplied by the distance parallel to the force or in the direction of the force, and the unit for work is joules, but you must use force in newtons and distance in meters. You cannot use any other units than the base SI units. It is a scalar quantity. It is not a vector. It has no direction. Work has no direction, even though force and distance have directions, but work does not have direction. The energy is defined as the ability to do work, and it is also in joules. So we can say that the work is equal to the energy, or the change in energy, or the transfer of energy. So work in joules is equal to energy also in joules. There are many forms of energy. There is potential energy types and kinetic energy types. Types of potential energy are gravitational, chemical, elastic, nuclear, and electric potential energies. The gravitational potential energy is the work done against gravity. Chemical energy is the energy stored in an object and can released by chemical reaction. Elastic or strain energy is the energy stored by a deformed object and can be released when the object returns to its original shape. Nuclear energy is the energy stored in a nucleus. Electric potential energy is the energy stored in charges. As for kinetic energy, it is the energy stored in a moving object. If the speed is equal to 0, the kinetic energy is equal to 0. If we're talking about kinetic energy of particles or molecules, this is called thermal or internal energy. If it's vibrations, we call it sound energy. If it's something called photons, we call it light energy. And if it's a moving charge or current, we use it electric energy. We call it as electric energy. Now, to understand the conservation of energy, we must know that for any system, there are three types of energy: input, useful output, and wasted energy. If you want to draw the flow of energy, there's something called a Sankey diagram. The original base of an arrow is the input energy, and the straight arrow, straight section that continues in a straight line, this is the useful output of the system or the machine. And the arrow that points downwards represents the wasted or lost energy. And the width of the arrows represents the amount of energy of input or output or lost. Now, to calculate the gravitational potential energy or the change in gravitational potential energy, we use the equation mgh. M must be in kilograms, the mass must be in kilograms. G, according to the field on Earth, it's 9.8 meters per second squared. And delta H, it must be the vertical height, not the inclined height. For example, if you have a drawing like this and it says that this is 5 meters and this is 3 meters, you choose the 3 meters, not the 5. The vertical height, and it must be in meters. If it's in centimeters, you divide by 100, millimeters, you divide by 1000. And the energy is always in joules. As for kinetic energy, the rule is half mv squared. Again, the mass must be in kilograms and the velocity must be in meters per second, but you must remember to square the velocity. Most people just forget about the square. You write it in the solution, but you do not use it on the calculator. So you must make sure that the velocity is squared and it's in meters per second. And again, the kinetic energy is in joules. If you are required to state something called the conservation of energy or the law of conservation of energy, you say that energy cannot be created nor destroyed. It can only transform or change form or change type. Another way of saying or stating this equation or this law is that the total energy remains constant, or the initial energy must be equal to the final energy plus the losses or the wasted energy. You can also write it as the initial gravitational potential energy plus the initial kinetic energy is equal to the final gravitational potential energy plus the final kinetic energy plus the losses. In most questions, you will find that either most of these are zero. For example, if you're required to ignore air resistance or ignore frictional forces, that means that losses are zero. If the initial motion of the object is at rest or the object starts from rest, kinetic energy initially is zero. If it stops, final kinetic energy is zero. If the final position is at the ground level, the final GPE is zero. If it ends If it starts from the ground, the initial GPE is 0. But in some cases, you should use all of these. In other cases, you are required to define this energy as a resistive force multiplied by distance. Since the losses are energy and energy is in joules, you can say that it is work done against a resistive force. For example, work done against air resistance or work done against frictional forces. So maybe you started from a height, so you have an initial gravitational potential energy, and you reach the ground. For example, you started from rest, so the initial kinetic energy is 0, and the final gravitational potential energy is 0 since there is no height at the ground. And you have the initial height, so you can calculate mgh, and you have the final velocity, so you can calculate the final kinetic energy, and the losses will be the difference between the initial and final energy. Then you're required to calculate the frictional force or the resistive force. You say that this lost energy is equal to the resistive force, which is unknown, multiplied by the distance traveled, which is the height you fell. This is how you calculate force, resistive force, when there is a question about energy changes. The next part is about power. The definition of power is the rate of doing work or the rate of transferring energy. So you can calculate it as work done divided by time. Rate of anything is over time. The work is in joules and the time is in seconds. It must be in seconds. And the power is in watts. Or you can say that it is a change in energy. It could be change in gravitational, kinetic, or thermal, or electric energy. Anything, you can use it in this equation. Then you divide by time. If the question says the rate of doing work or rate of transferring energy is a certain number, it means power. If you are required to calculate the rate of doing work or the rate of transfer of kinetic energy or the rate of change of kinetic energy, it also means power. So if you want to calculate work, you can use force times distance. So power is force times distance over time. Or distance over time in a certain direction, which is parallel to the force, is called velocity. So we have three equations: work over time, force times distance over time, or force times velocity. And all these you must use the SI based units of the quantities. Next, we take efficiency as a definition is equal to the equation. It is the useful energy output over the total energy input, or useful power output over total power input. You do not mention the wasted energy. If, for example, you have a wasted energy, for example, you have a power input equal to 100 watt, and wasted energy or lost power 50, let's make it 60 watt, and you want to calculate the efficiency. Using this equation, the output or the useful output is equal to 100, the input minus the wasted energy, then you divide by the total input, which is 100. You can calculate it as a fraction as it is, or you can multiply it by 100 to get a percentage. Sometimes it is left to you to decide whether to multiply by 100 or not. Sometimes the dots of the solution, you are required to calculate it in percentage if you see this sign. The last section is about the energy resources, not types of energy resources or sources of energy. A renewable resource is the source that has a continuous supply of energy, or that it does not run out, or it can be replaced once used. A non-renewable source of energy, it is a form of energy that will run out once used, or there is no continuous supply or cannot be replaced once used. The types of renewable energy, we have first type is the solar energy. We can use solar cells to generate electricity, so we convert light energy into electrical energy. Or solar panels that use heat energy from the sun, from the radiation of the sun, to heat up some water. In this type of energy resource, we have several advantages. It is a clean and renewable source of energy. It causes no pollution or emits no harmful gases. It has low running cost. Once set up, you do not have to burn fuel or use any other equipment to maintain the system. But disadvantages is that it is not reliable. You cannot control the amount of energy. It has low efficiency. The amount of energy output is low compared to the input, and it is dependent on the daytime and the weather and the location of the area you are using it in. The next renewable resource is hydroelectric power stations. We use the gravitational potential energy stored in water behind the dam to fall and gain kinetic energy and then spin a turbine which is connected to a generator. So from GPE to kinetic energy in the turbines and generator, and the generator converts this kinetic energy into electrical energy. In a hydroelectric power station, the advantages are it is a renewable and clean source of energy. It is reliable. You can control the amount of energy. It has high efficiency, but it is very expensive and dangerous to build. It has high running cost and high initial cost, and it causes flooding behind the dam. If you are required to say how is this dependent on the sun, is this source dependent on the sun, you can say that the collected water is from rain falling from clouds that are formed by evaporation from seawater, and the evaporation depends on sunlight. As for tide energy is a form of energy that depends on the difference in levels of waters, just like the hydroelectric power station, and it follows the same conversion of energy and advantages and disadvantages, except it has low efficiency and it is not reliable. You cannot control the amount of energy output. Waves energy are the same thing, but it uses the kinetic energy of waves moving up and down caused by the winds to generate electricity. This is also dependent on the sun. The tide energy is actually dependent on the moon, not the sun. Wind depends on the difference in temperature between parts on the planet, and the difference in temperature is caused by the sun pointing towards one side and away from the other side of the planet. The next renewable resource is wind turbines. In wind turbines, the wind is required to rotate a turbine which is connected to a generator. So the kinetic energy is converted to kinetic energy in the turbine and generator, and then generator converts it to electrical energy. It is a clean source of energy, non-polluting. It has low running cost, but it has a very high initial cost. It is unreliable. It depends on weather and location, and it has low efficiency. So it actually it's very bad or very low level output, and it actually affects bird life since it kills many birds every year. The last of the types of renewable energy are the geothermal energy and the biofuel. They both follow the same scheme that you boil water, and this water is converted to steam with a high pressure. They flow through a turbine. The turbine rotates a generator, and the generator produces the electric power. So we use the heat energy, and we convert it to kinetic energy, and the generator converts this kinetic energy to electrical energy. In the case of geothermal power station, we use the heat from the ground. Underground, there are rocks that are at a very high temperature, well above the boiling temperature of water. We send water downwards, it boils and comes back through pipes, and the pipes are directed towards the turbine, so the turbine rotates. In this scheme, it is a renewable source of energy, clean source of energy. It has actually a very high initial and running cost since water causes rusting to the equipment, and it is limited by location. You must be near a very hot area or a deep area, so you don't have to dig a long distance downwards to reach the hot rocks. But it is very dangerous because you can encounter radioactive materials while digging, or an active volcano while digging. As for biofuel or biomass, we call it biomass, we instead of digging underground, we burn some animal waste or dead plants or dead bodies of animals just to generate the heat that will boil the water and then convert it to steam. But it is the same scheme. For fossil fuels in general, we are required to know that these fossil fuels are made from dead bodies of plants and animals for over a long period of time due to the pressure and the heat underground. And we are required to know that at the first position, we use chemical energy and we convert that energy into heat. It is the same scheme as the geothermal and biomass, but instead of digging underground or burning dead animals and plants that are recently dead, we use oil or coal or natural gas, and we convert that chemical energy into heat energy, then to kinetic, then to electric using the generator. Fossil fuels are considered non-renewable since they will run out eventually if we use them as fast as we are using them now. They are polluting. They emit carbon dioxide, which causes global warming or contributes to global warming, and carbon monoxide, which is actually poisonous. And there is a very high running cost. Every time you need to burn something, you need to dig for fuel and treat the fuel so it produces a large amount of energy. Then you need to transport the fuel to the place where you burn the fuel and convert it to steam. And there is a low running cost. It is available. You can find oil and coal almost anywhere. It is available and it has low initial cost but high running cost. As for nuclear fission, it is a last source of energy. It is non-renewable since nuclear materials, when you use them, they are converted into different or new elements, which means you cannot use them again as the same element. For example, uranium is changed into krypton and barium. So you no longer have uranium once you use it, so it is non-renewable. There is no continuous supply of nuclear materials. And fission is actually the splitting of nuclei into two new nuclei. It is a clean source of energy. It is non-polluting, but there is also the risk of explosions and radiation leaking outside the nuclear power station. You use this heat from the nuclear reaction to heat water, to boil it to steam, and then turn the turbine and so on. So this causes a change from nuclear energy to heat energy to kinetic energy, then to electric energy from the turbine to a generator. The next chapter is about pressure. The definition of pressure is force per unit area, and the equation of pressure is force divided by area. The force is always in Newton, and the area must be in meters squared. So a unit for pressure could be newtons per meter squared, but we use the unit Pascal. That's when the force is in newtons and the area is in meters squared. If you have any two objects in contact with each other and you need to increase the pressure, for example, you need to use a knife to cut through something. Why do you use a knife? Because it has low contact area, so the pressure is great or high. Or the skates or the wide boots we use on ice are used to increase the area or the contact area with the ice, which causes the pressure to decrease, so the ice is less likely to crack or break under the weight of the wearer. The pressure in liquids is a little bit different from the pressure in solids. The pressure between solid objects depends on the direction of the force you apply, but in liquids, the pressure actually acts in all directions, even though it is due to the weight of the liquid above an object, but it acts in all directions, not just downwards on the object. Also, the pressure increases as depth increases. So the pressure here is low, the pressure here is moderate, the pressure at the bottom will be the highest. We use the concept of pressure dependent on the depth to understand something, that it does not depend on the shape of the object or the area of the object. The area here is different, but the pressure is all the same. All these have the same pressure. It only depends on the type of liquid and depends on the depth of the liquid. Since the depth is the same and we have the same liquid, you have the same pressure. The equation for pressure in liquids is rho, which is the density, g, the gravity acceleration, by h, which is the vertical depth. it is measured from the top to the bottom, not from the bottom to the point. For example, this is the surface of the liquid, and we are required to measure the pressure at this point. We measure this distance, not from the bottom. It is calculated from the top, from the surface of the liquid downwards, not from the base of the liquid upwards. And the density must be in kilograms per meter cubed. So if you have it in grams per centimeter cubed, you multiply it by 1000. The gravity on Earth is 9.8. If you are on another planet, or it is mentioned that you have a different gravitational field strength, use the field strength in the question. And the depth is always in meters, not in centimeters, not in millimeters. For hydraulic systems, we must understand that liquids are incompressible. That means that their volume remains constant if the temperature remains constant. So if you apply pressure at one point in a liquid, this pressure is transmitted as it is through the whole liquid. So if you have two positions, position 1 and position 2, and you apply pressure here, the same pressure will be applied on the other end, and the same pressure will be applied through the whole liquid. This causes the force to be different if the areas at the ends of the pipes are different. For example, if the pressure here is equal to the pressure on the other side, then the force on the initial side divided by the area is equal to the force at the second side divided by the area. If the areas are different, then the forces are different. Since we have division, force over area, this means that the force and area are directly proportional. So if area increases, the force also increases. So this is a small force, this is a large force, since the area is greater. If you are required to explain why the force is greater, you can either use the concept of the pressure is the same, so the force depends on the area, or use the equation force is equal to pressure times area, and then you say pressure is constant, so as area increases, force increases. Also, you are required to explain something that if you have a smaller area, you have to move a longer distance. If you have a larger area, you move a smaller distance. To explain this, you either use the concept of energy conservation. You say that the energy input is equal to the energy output. So energy is equal force times distance, which is the work. If the force increases, the distance decreases. Or you use the concept of the constant volume, since liquids are incompressible. Volume is equal to area multiplied by length. So if you increase the area, the length decreases. If you increase the length, the area decreases. Next, we talk about something called upthrust. This is due to the change in depth of an object inside a liquid. So the pressure below an object would be higher than the pressure above the object. That's what causes a resultant force upwards. So this upward force depends on the difference in pressure between above and below the object. So the change in pressure multiplied by the area is equal to the upthrust force. Since force is equal to pressure times area, the change in force is equal to the change in pressure multiplied by the area. And the area here must be in meters squared, and the pressure in Pascal to get the force in newtons. If this upthrust force is greater than the weight, the object will float, will rise upwards. If this upthrust force is less than the weight, the object will sink downwards. And this happens when the density of the object is greater than the density of the liquid. Next, we talk about atmospheric pressure. The atmospheric pressure is the weight of a column of air acting per unit area. Unit area means 1 meter squared of area. So the column of air above 1 meter squared until the edge of the atmosphere has some molecules of air in it, and they have weight acting downwards on that area. If you calculate that pressure, it is approximately 100,000 Pascal, just to make sure that you are calculating it correctly. But that is at the sea level or the sea surface level. If it's on another level, say for a mountain, it would be less. In a valley, it would be more. So the higher you get, the less atmospheric pressure you have. The lower you get, the more atmospheric pressure because you have more air molecules above you. If you have a proof of the existence of atmospheric pressure, for example, if you have hot gas or hot air inside a can and then you cool the can, suddenly it contracts or collapses because the atmospheric pressure outside will be greater than the pressure of the gas inside. At first, the two pressures were equal to each other, so they have equal forces on the edge or the wall of the container. Now, as the gas cools, its pressure decreases, and there is a resultant force inwards on the container. Okay, now we go to thermal physics. The first chapter is properties of matter. First, we mentioned something called the kinetic model of matter. The kinetic model of matter states that any object or any substance is made of millions or billions of molecules that are in continuous motion. And the type of motion and the type of the forces between the molecules controls the properties of the matter. There are three states of matter that we have in the syllabus. There is a fourth state called plasma, but we only have solids, liquids, and gases. And we need to know the differences between these states in terms of intermolecular forces. The forces in solids and liquids are very strong, but in gases they are almost negligible or almost zero. In liquids, it is slightly weaker than in solids. Okay, when talking about intermolecular spaces, the spaces between molecules in solids and liquids are very small, or they are tightly packed. Molecules are tightly packed to each other. In gases, the spaces are much wider between molecules. The movement of molecules in solids is vibration about a fixed position or vibration in place. In liquids, we say that they translate and vibrate, or they slide over each other. In gases, we say that the motion is completely random at different speeds and there are collisions between the molecules. For the speed differences for one material from solid to liquid to gas, in solids the speed is the minimum or the slowest speed. In liquids faster, in gases much faster, and they have different speeds. As for the arrangement of molecules in the object, for a solid object we have a regular long range arrangement, or the shape of the molecules should be a specific sequence. In liquids and gases they are random or irregular, or no regular arrangement in liquids and gases. These are for the molecules or the infrastructure or the microstructure of the objects. As for macrostructure of an object as a whole, we say that solids and liquids have fixed volumes. Gases depend on the volume of the container. As for the shape of the object, for solids they have fixed shapes. For liquids and gases they depend on the shape of the container. Now we go to something called Brownian motion. If you are required to describe the motion, you just say that there is random zigzag motion of suspended particles in a fluid. It could be dust or smoke particles in air or pollen grains in water. If you are required to explain Brownian motion, for example, if you have smoke or dust in air, you say that when the small air particles or molecules collide with the smoke or dust particles, there is a change in momentum due to rebounding, which exerts random forces on the object and pushes it to move or causes random motion. If you increase the temperature of the gas or the liquid, the motion becomes faster and more random because the molecules gain kinetic energy. If you increase the size of the smoke particle or the dust particle, the random becomes slower, but not because the mass increases. It is because that the collisions will be on a larger area and will cancel each other. More collisions will cancel each other. Now we go to a definition of temperature and internal energy or heat energy. The temperature is a measure or proportional to the average kinetic energy of molecules. Average means energy of one molecule. One of the molecules has energy. The average energy represents the temperature. So the faster the molecules move, the higher the temperature. But if you calculate the sum of kinetic energy and potential energy of all molecules, potential energy is because of the intermolecular forces. If you calculate the total energy, you get something called the internal energy. So the internal energy is the sum of energies of all molecules. The temperature is a measure of the average kinetic energy of a molecule. If you put two objects with different temperatures side by side or near each other, energy will flow from the hotter object to the cooler object until both objects are at the same temperature. This is called thermal equilibrium. So the definition of thermal equilibrium is that energy flows from the hot object to a colder or a cooler object until both objects are at the same temperature or all objects are at the same temperature. Now we must understand the concept of expansion. Expansion means increase in volume. If thermal expansion is in question, you talk about the increase in volume due to the increase in temperature. So how do molecules expand? When temperature increases, the kinetic energy of the molecules increases. They collide more often with greater force and push each other apart. But the size of each molecule itself does not change. The spaces between molecules increases. There is something called expansivity. It means how much expansion happens per degree Celsius or per Kelvin. If you have, for example, iron and you have copper, copper expands more than iron for the same change in temperature. If the change in temperature in both is, for example, 1 degree Celsius, the change in volume in copper will be greater than the change in volume in iron. So we say that copper has higher expansivity. When you build machines and when you build roads and objects that fit together, you must allow for expansion and different expansivity. It is better to build something with materials that have close expansivity than to have different expansivity. If you have different expansivity, when temperature changes, the materials will crack because some of them want to expand more than others, so they will bend and eventually break. Which means that you need to allow for expansion by leaving gaps between objects or using rollers that will help the movement between parts of an object or of a machine or a structure during expansion and contraction. If you're asked about why cables on the road are left slacked, that is to allow for contraction, not expansion, because when temperature decreases, the wire will be straightened out because its length will decrease as volume decreases. So we don't want them to snap at the edges of the cable. Another idea about different expansivity is the use of bimetallic strips. Bimetallic strips are strips made of two metals with different expansivity, but they are welded together, so they have to move together. So if one of them wants to expand more, it will bend towards the lower expansivity. So expansivity here is lower, expansivity here is greater. The one that expands more also contracts more. So contraction is greater on the copper side or the one with the higher expansivity, it has higher contraction as well. We can use these strips as switches in electrical devices that depend on temperature. For example, if you reach a certain temperature, the switch will bend away from contact with the other components of the circuit, so it opens the circuit and the circuit stops working. When the temperature cools down again, the bending will be in the opposite direction, so it closes the contact again and the circuit works again. Expansion in liquids is a bit different since liquids don't have a specific shape. In solids, all dimensions must expand. Length, width, and height must all expand. But in liquids, you can expand in 1 dimension or 2 dimensions only. You don't have to expand in 3 dimensions. But there is also the effect of change in density that appears in liquids since the change in volume in liquids is greater than in solids. So solids expand less than liquids, liquids expand less than gases. Or in reverse, gases expand more than liquids, liquids expand more than solids. So if you expand something, if the temperature of an object increases, especially liquid and gas, the volume increases, so the density decreases. If you have part of a liquid that is less dense than the rest of the liquid, this part of the liquid will float, will rise upwards, and will be replaced by the colder liquid, which is called convection. There is a special case when changing the state of an object. Usually, all matter, when changing state from solid to liquid, they expand, or from liquid to solid, they contract. Except water, when it freezes, it leaves an empty space. So actually, in water, volume increases when it freezes. This is the only material that does this behavior. That's why ice is more light or less dense than water. That's why ice floats on the top of water. As for gases, when we mention expansion, we must understand something, that gases exert pressure on their containers. If you are asked how a gas exerts pressure on the walls of a container, first you must mention that gas molecules move randomly and collide with the walls of the container. And these collisions cause a change in momentum, and the change in momentum exerts a force over the area of the container. So the force exerts pressure. But how does gas expand? If you have a container that is elastic, or for example, like a balloon or something that can expand, if temperature increases, the rate of collisions increases. So rate of collisions increases, so the momentum also increases. So rate of collision and momentum increase. This increases the pressure inside the balloon or inside the container. So the pressure inside the container will be greater than outside the container. So there will be a resultant force outwards, so the volume increases. But when volume increases, the rate of collisions decreases again, and the pressure decreases again. But in general, when temperature increased, the volume increased. So first, temperature increases the rate of collisions and momentum, which causes the pressure inside the container to be greater than outside, pushing the volume outwards. But as volume increases, the pressure decreases again. But in general, we expanded by increasing the volume. The last part about this chapter is the gas laws. There is Boyle's law, which is a constant temperature gas, or constant amount of gas at constant temperature, and you change the volume and see what happens to the pressure. If you draw a relationship between pressure and volume at constant temperature and constant amount of molecules, you will find that the pressure and volume are inversely proportional. Or if you have two situations or two states, 1 and 2, if you multiply P1 by V1, you will get the same answer as P2 times V2, or P1 V1 equals to P2 V2, or PV is constant, does not change. That means that they are inversely proportional. If you keep the volume constant with a constant amount of gas, you will find that as temperature increases, the volume with the volume constant, the pressure also increases. But if you draw a graph of the temperature in degrees Celsius with volume or pressure, you will find that it is not a straight line going through the origin, and it is not an inversely proportional curve. Since it is a straight line that increases with both axes, or a positive gradient, you can just extend that line to a point where they meet, where the axis meets. You will find that it will be negative 273 degrees Celsius. This is called the absolute zero. An absolute zero is the temperature where the molecules have no kinetic energy. That is why they have no pressure. If they are not moving, they are not colliding, so there is no force and there is no pressure. So absolute zero means the temperature at which the molecules have no kinetic energy, and this temperature is called 0 Kelvin. So the temperature of 0 Kelvin is equal to negative 273 degrees Celsius. To convert from temperature in Celsius to Kelvin, you need to add by 273. And you do the reverse to convert from Kelvin to Celsius. If you want the temperature in Celsius, you subtract 273. Now, if you draw the graph of pressure against temperature in Kelvin, you will find that it is a directly proportional relationship, or P1 over T1 is equal to P2 over T2, but temperature must be in Kelvin, not in Celsius. It is not repeated as much as P1 V1 equal P2 V2, but it is in the syllabus, so you might be one of the lucky ones that will receive this equation in the first time since about 20 years. Lastly, there is a Charles law, which says if you have a constant amount of gas and you keep the pressure constant and you test volume against temperature, we already said the concept that as temperature increases, the volume increases. But still you have the same idea about the graph meeting at negative 273. So it is the same rule, V1 over T1 is equal to V2 over T2 with the temperature again in Kelvin. If you are required to explain these phenomena in terms of molecules, if you go to Boyle's law, where the temperature is constant, you say that as volume decreases, the rate of collisions increases. No mention of kinetic energy since temperature is constant. Temperature represents kinetic energy and temperature was constant, so do not mention kinetic energy of molecules. Only mention the rate of collisions, and as volume decreases, also area decreases. So rate of collisions increases over a smaller area, that causes the pressure to increase. As for the pressure law, as temperature increases, molecules gain kinetic energy, collide harder or with greater momentum with the walls of the container and more frequently. So the pressure increases. As for the last part, we said it already, temperature increases, the pressure inside the container increases, pushing the volume outwards. Then as volume increases, the pressure returns to its original value. That's why the pressure is considered constant. Pressure increases first, then decreases when volume increases. The next chapter is about heat transfer. Heat transfer depends on something called the rate of heat transfer, and it depends on the difference in temperature between two objects. For example, if one object is at 80 degrees Celsius and the other is at 20 degrees Celsius, the rate of heat transfer will be high. If one is at 40 degrees and the other is at 20 degrees, the rate of heat transfer will be low. That's why if you leave an object in a room with a room temperature of about 25 degrees Celsius, any temperature between 20 and 26 degrees Celsius is acceptable for a value or an estimate of room temperature. And you start from a high temperature. On the y-axis, you will find that the graph will be a decreasing gradient graph. It will be like this. It starts with high gradient, then the gradient decreases. As the difference between the temperature of the object and the surroundings decreases, the rate of heat transfer decreases. The other thing that affects the rate of heat transfer is the material itself or the type of heat transfer process that occurs, which is either conduction, convection, or infrared radiation. The definition for conduction is the flow of thermal energy between particles due to collision between neighboring particles. So the particles with higher kinetic energy collide with the adjacent molecules or the neighboring molecules and transferring part of their kinetic energy with them. If you are required to explain an extra process that happens in metals as good conductors, other than collisions between molecules, they have free electrons that are transferred between molecules with higher energy and molecules with lower energy, and also transferring some of the kinetic energy, so the temperature of the next molecules increases. Generally, materials of good conducting properties or good conductors are used when you need the temperature to change quickly or the rate of heat transfer to be fast. Poor conductors are materials that do not allow flow of thermal energy, like plastic, wood, rubber, glass, and so on. Air is one of the worst conductors. Vacuum is the worst conductor. You cannot transfer heat energy through vacuum by conduction because there are no molecules, so no collisions between molecules. And poor conductors are required when the rate of heat transfer is required to be low. Now there are several experiments you can use for testing which material is better conductor or worse conductor. You can use the first example here, 4 rods with different materials and equal dimensions for fair comparison are all placed at one side in a flame to make sure that the temperature at one side is the same for fair comparison again. and use, for example, thermometers or wax that will melt on the other end, and you see which one will reach the other end, which one has the heat reaching the other end faster. So the wax melting means that the temperature is higher now. So it is an indicator of which one will fall faster, so which one is a better conductor. Or you can choose two materials and use a flame and a piece of paper that will burn if the temperature gets high enough. But for a good conductor, heat is transferred away from the paper, so it will not change color, it will not burn. But for a poor conductor, the temperature cannot uh, be lower because heat is trapped in this area. It cannot flow away from the paper, so the side of this paper on the poor conducting side will be burned much quicker. As for water, it is said to be a poor conductor. Heat cannot travel through water by conduction very quickly. It is a poor conductor, but it will travel by another method, which is called convection. In convection, if you heat a fluid which is a liquid or a gas, it becomes less dense because its volume increases, it expands, so the volume increases, and it becomes less dense. The less dense part of the liquid rises, and the more dense part of the liquid falls. So heated liquid becomes less dense and rises. Cooled liquid becomes more dense and falls or sinks downwards. And the continuous flow between hot and cold fluid is called a convection current. Now we can see this in liquids or gases. So in this case, we have the candle burning, causing the air around it to be hot, and the hot air rises upwards and carries smoke with it. So the other end with the cold air has to replace this empty space and causes the cooler air to fall down, which is more dense than the other side. So it pushes the smoke down. In general, the smoke should be moving upwards from around this burning piece because the burning piece is hot and causes the air around to be hot and sort of carries the smoke upwards. But in this case, the convection current forces the smoke to go in this direction. A natural convection current appears on the shores of seas or lakes. Water cools and heats up much slower than sand because sand has low thermal capacity. It needs a little energy to rise in temperature. So when the sun rises, the sand becomes much hotter than the water at a very short time. So the hot air above the sand rises and cold air from above the water replaces it. This is the day breeze towards the land, and cold air from above the sea falls down, and the cycle is completed from above. At night, when the sun stops shining, the sand cools much quicker than the water, so now water has hot air above it, which rises, and cold air comes from land towards the water, and the cycle is reversed during the night. We also use convection currents in refrigerators. We place freezers at the top to conserve energy. You only need to cool the freezer, and the cold air below the freezer will cool the rest of the refrigerator. Or you can place a heater at the bottom of a room, so the hot air will rise upwards, and the heater only has to heat the air at the bottom, and by convection, the hot air will rise and replace it by cold air. So you do not have to project the hot air in the room. You can use convection currents, which saves energy. As for the third method of heat transfer, it's called infrared radiation. We must say it is infrared radiation, and it is the flow of thermal energy by electromagnetic waves. Heat radiation is electromagnetic waves. It has certain properties. It can travel through vacuum. Conduction and convection cannot flow through vacuum. That does not mean that radiation does not flow through other materials. Radiation can travel through anything, solids, liquids, and vacuum, and gases. But in vacuum, it has the highest speed, which is 3 times 10 to the power of 8 meters per second. It can be emitted, reflected, absorbed, like all other waves. But the most reflection happens when the surface is shiny. The most absorption or emission happens when the surface is dull or black. So the color affects heat radiation or infrared radiation. The shinier the surface, the better reflector or the poorer emitter and absorber it is. So poor emitters and absorbers are good reflectors. But good emitters and absorbers need to be dark or dull. Also, to emit and absorb a lot of energy of infrared radiation, the surface can be wide or larger area causes the amount of infrared radiation to increase. Also, objects with higher temperature emit more infrared radiation. So it depends on color, surface area, and temperature. The higher the temperature, the darker the color, and the larger the area, the greater the amount of infrared radiation emitted or absorbed. If you are checking which surface is a better absorber of heat radiation, you need the surface to be cold, so these surfaces are cold, and you need an external source of heat. To test the theory, you must check that there is no conduction, so no contact between the surfaces and the heater, because conduction happens through contact, molecules that are adjacent or next to each other, and no convection, so you do not place these surfaces above or below the heater. You place them by the side. So if you're testing something by the side, at the side of a heater, or not in contact, you are only testing infrared radiation, not conduction and convection. So for best results of comparison, you must make sure that the initial temperature of the surfaces are the same, areas are the same, materials are the same, and the distance from the heaters or the heater, one heater is better, is the same. If you are testing emission, the object itself must be hot, not cold, and it radiates heat outwards. To test the theory of amount of radiation, if you are going to test colors, for example, you must make sure that the temperature is the same, the material is the same, but the color is different. If you are going to place a detector, you must place detectors at equal distances and make sure that the room temperature is the same for all of them. Now, to explain the concept of greenhouse effect or the global warming, the idea is the amount of radiation that is incident on an object is less or more than the amount of heat released. If it is more than released, then the temperature of the object will keep rising because you're receiving more energy than you are releasing. And this is the case in greenhouses and on our planet, on the Earth. The greenhouse effect means that the amount of energy incident on the planet is greater than the amount of energy released from the planet or from the greenhouse. So the temperature keeps rising. The last part in this chapter is about insulation. If you want to insulate a building or a house, you need to consider several options. You can use double glazed windows or double walls or cavity walls, which basically creates a poor conducting material between two walls, whether they are made of glass or made of bricks or concrete. The poor conducting material decreases the amount of energy transfer by conduction. Or you can place a vacuum in between that prevents conduction completely between the two walls or the two panes of window. You can also use loft or under loft materials, which are basically lagging or insulating materials above or below a room, above the ceiling or below the floor of a room. This decreases also the amount of energy lost by conduction. Same as carpets, curtains, and draft excluders. Draft excluders prevent the wind that flows through the holes or the gaps between the doors and windows and the walls. And curtains trap air between the window and the curtain, so the air cannot circulate, so you're decreasing convection, and also air is a poor conductor. You can make the curtains brightly colored, so they can also reflect infrared radiation or be poor emitters or poor absorbers of heat radiation. This type of device, the vacuum flask, is said to be the ultimate insulation because it has silvered surfaces which reflect infrared radiation, or if you have a hot liquid inside, infrared radiation is not allowed to be emitted. They are poor emitters. Or if you have a cold beverage inside, heat cannot be absorbed because the silver surfaces are poor absorbers of heat radiation. And between two containers, there is vacuum. Vacuum decreases conduction and convection. And the outer body of the object is made of a poor conducting material to decrease rate of heat transfer by conduction. And the stopper at last decreases convection and evaporation. If you have a cold liquid, you do not need a stopper to decrease convection, because a cold liquid will have cold air above it, and cold air remains at the bottom, does not rise. The problem is when you have a hot liquid, the hot air above will rise and be replaced by cold air, which will steal more heat by conduction from the liquid. The next chapter is about thermal energy. Thermal energy can be produced on our planet using friction, fire, or by burning fuel, or by electric heaters. If you have an electric heater, it will probably have its own power branded on the heater itself. All you need to calculate the energy is you multiply the power by the time. Since power is equal to energy divided by time, so energy is equal to power multiplied by time. So the power must be in watts and the time must be in seconds to get the energy in joules. Usually we call the thermal energy Q for to specify that this is thermal energy, not any type of energy. There is something called thermal capacity. It is the energy required to raise the temperature of an object by 1 degree Celsius. So if the thermal capacity is the energy to increase temperature by 1 degree, and you have several degrees to increase the temperature, you can just multiply it. If you have thermal capacity 500 joules per degree, and you need to increase the temperature by 10 degrees, then you multiply 500, which is for 1 degree, by 10, you get 5,000 joules in total, which is the thermal energy. So this is the energy per degree Celsius. This is the number of degrees Celsius. You get the total energy. Another type of capacity is the specific thermal capacity, which is repeated much more in the exams. The specific heat capacity or thermal capacity is the energy required to raise the temperature of a unit mass of a certain substance, not an object as a whole. It must be all made of the same material. For example, a cylinder all made of iron or all made of copper, and again by 1 degree Celsius. So if this is the energy per degree Celsius, you need to multiply by the number of degrees Celsius. And this is the energy per kilogram unit mass. You must multiply it by the number of kilograms, which is the mass, to get the total energy. So if you have an object not made all of the same material, use that the energy is equal to the thermal capacity by the change in temperature. If you have an object all made of the same material, you say that the thermal energy is equal to the specific heat capacity by the mass by the change in temperature. And the unit for thermal capacity is joules per degree Celsius, and the unit for specific thermal capacity is joules per degree Celsius kilogram, or kilogram degrees Celsius. Also, if you have the change in temperature in Kelvin, it is the same as the change in temperature in Celsius. So for changing from 25 degrees to 30 degrees, that you increase the temperature by 5 degrees, you are also increases the temperature by 5 Kelvin. So delta theta or delta T is the same thing. If you have an experiment in paper 4 that requires to measure the specific heat capacity, you need the energy, but there is no device to calculate energy. There is only a heater and a timer. So you calculate the power and time multiplied by each other to get the energy. Then you divide by the mass and the change in temperature. So the readings required are the heating time, the power is given, or you can calculate it as voltage multiplied by current. If you have an electrical method, use a voltmeter and an ammeter to calculate the power. Then you divide by the mass of the object, then multiplied on the denominator by the change in temperature. So you need the initial and final temperatures of the object, and finally the mass of the object must be measured using a balance. If you have a liquid, the only different thing is you cannot measure the mass directly. You must measure the mass of the empty container, then the full container, then you subtract to get the mass of the liquid itself, then you use the same equation. In these experiments, there are always false results if there is heat gained or lost. If there is heat lost, the value of C will be greater than normal. If there is heat gained, the value of C will be less than normal. This is because the time of the experiment will increase. Since you are losing heat to the surroundings, you will not be able to heat the object to the required temperature in the same time. You will have to take longer time to heat the object and the surroundings. If the object is colder than the surroundings are helping the experiment to move along faster, so you're gaining heat from the heater and from the surroundings, so the time of the experiment will be lower. That will cause the value will be to be lower. If you want to avoid this problem, you can use insulation around the object to prevent heat loss or decrease heat loss or heat gain from the surroundings. Now, if the temperature is not changing, but you are still supplying heat, that means that there will be a change of state. Melting or boiling if the temperature is given to the object, or freezing and condensing if the temperature, if the heat is taken away from the object. So, as a fact, since temperature will be constant, the kinetic energy must be also constant. So when increasing temperature, you say that the thermal energy is giving kinetic energy to the molecules. So the molecules move faster. You cannot say this in melting, boiling, condensing, or freezing. Since the temperature is constant, so there is no change in kinetic energy. But what happens to the thermal energy supplied or taken? This thermal energy during melting or boiling is used to break the intermolecular forces between the molecules and increase the spacing between them. Or saying that the thermal energy is converted to work to increase the spacing between molecules. So work is equal to force times distance. Force is the intermolecular forces, and distance is increasing the spacing between the molecules. For cooling curves, the temperature decreases, but still at condensing, the temperature remains constant, and still at freezing, the temperature remains constant. Coming to evaporation, that's also a change in state, but it is not the same as boiling. It is a change from liquid to gas. But how does a liquid change into gas at a temperature other than the boiling point? You say that the most energetic molecules at the surface gain enough energy to break the intermolecular forces and escape from the liquid. They either gain this energy using a heater, an external heater, or gain it from the molecules that collide with them from the bottom side of the liquid. But they gain enough energy to break the forces and escape from the surface of the liquid. We must mention that the most energetic molecules escape, and that they escape from the surface, and that they gain enough energy to break intermolecular forces. Now, to increase the rate of evaporation, you can increase the temperature, which increases the energy, so it is easier to escape. You can increase the surface area, so more molecules will be at the surface. You can reduce humidity, which decreases the concentration of vapor in the surrounding air, so it will be easier for more vapor to be formed. Or blow wind over the surface area. Blowing wind decreases the humidity. It removes the water vapor from above the surface. Now there are differences between evaporation and boiling. Evaporation occurs only at the surface, but boiling occurs through the whole liquid. Evaporation occurs at any temperature, but boiling occurs only at the boiling point at a specific temperature. For similarities, both are a change from liquid to gas, and both require energy. But boiling requires a heating element, an external heater, but evaporation can take energy from anything. It can take energy from the rest of the liquid or from a nearby object it is in contact with. So, for example, water on the surface of the skin of a person, it absorbs energy by conduction from the skin to break intermolecular forces and escape. Molecules at the surface of liquid in a container, they absorb energy from the other molecules in the container, which causes a cooling effect. Since the most energetic molecules escape from the surface of the liquid, the rest of the molecules will be at a lower average energy. Since the molecules with the higher energy left, the average will be lower. Also, if you test the theory on skin, for sweating, when water evaporates from the skin, sweat evaporates from the skin, it absorbs energy from the skin. So the kinetic energy of molecules of the skin decreases, so the temperature of the skin decreases, which causes a cooling effect.